Welcome back to the deep dive. Today we are going to do something a little different. We are grabbing a wrench, we are popping the hood,
Yep.
we are completely ignoring the shiny paint job
hmm
and looking directly at the engine block.
Which, frankly, is long overdue. Usually when we look at the source material and artificial intelligence, everyone wants to talk about the magic.
Right.
You know, the chatbot that writes sonnets in the style of Shakespeare or the image generator that wins state fairs. It's all very Arthur C. Clarke.
Sufficiently advanced technology being indistinguishable from magic.
Exactly. But we are here today to ruin the magic trick. Or maybe not ruin it, but to explain how the trick actually works so you can appreciate the incredible dexterity required to pull it off.
I like that better.
Because the sources we've pulled for this deep dive suggest something really fundamental. If you treat deep learning as a black box, if you just stack software layers like Lego bricks and hope for the best, you don't get intelligence, you get noise.
I feel seen. I feel attacked. That is literally how I thought it worked. You download a library, you stack some neural layers, you hit run, and boom, AI.
You and about 90% of people entering the field. But the mission of this deep dive is to debunk that. We are going to look at the invisible engine room. We're digging into the math, the statistics, and the machinery that makes this stuff function. It isn't just coding. It's a complex interplay of three specific disciplines. Statistics, which is all about understanding the reality of your data. Calculus, specifically optimization and how we learn. And, engineering, the architectural frameworks that keep the whole thing from collapsing under its own weight.
It's the difference between knowing how to drive a car and knowing how to rebuild the transmission in your garage. And to hook you in right at the start, listener.
In reviewing the research for this, we found some concepts that are honestly kind of terrifying. We're going to talk about silent failures.
That phrase alone should make any engineer sweat. It should. It's how an AI model can be 100% confident in its answer and yet completely disastrously wrong because the world around it changed and it just didn't notice.
That is the stuff of nightmares for data scientists. It's the unknown unknown. You don't know that you don't know.
And on the flip side, we're going to talk about moving dirt.
Yeah.
Literally. A mathematical concept called Earth Mover's Distance, involving piles of dirt that turns out to be the secret sauce behind generating realistic images.
It is a beautiful example of how a very abstract 18th century math problem solves a hypermodern tech problem. It's really poetry in mathematics.
So here is our roadmap for the hour. We have three main pillars to get through. First, statistics and reality. We'll look at how data changes and breaks models, a concept called drift.
Super important.
Second, the math of learning. So how do we measure the difference between two things? And how do we optimize the brain of the AI? And third, the frameworks. This is the hardware and software war dynamic graphs versus static graphs, and how to train models that are bigger than a single supercomputer.
It sounds dense, I know. But once you see how these pieces fit together, it's incredibly satisfying. It removes the mystery and replaces it with, I think, a real engineering appreciation.
Let's jump in. Part 1. When good models go bad.
Let's set the scene with a scenario. We need to visualize this.
Okay. Scenario. I am a machine learning engineer. I build a model. Let's keep it high stakes. It detects pneumonia in chest x-rays.
Okay, serious business. No room for error there.
Right. I train it. I test it. It gets 99% accuracy. I am a genius. I deploy it to a hospital system. Everyone loves it. 6 months later, I check the logs, and the model is useless. It's missing diagnoses everywhere. It's flagging healthy lungs as sick. It's a mess. But I didn't change a single line of code. What happened?
You didn't change the code, but the world changed. This is the classic problem with the set it and forget it mentality in AI. You, my friend, fell victim to drift.
Drift. It sounds like something a car does on a racetrack, or maybe continental plates moving apart.
In this context, drift refers to the degradation of a model's performance over time due to changes in the environment or the data itself. It's the entropy of the real world seeping into your sterile mathematical system. The model is static, reality is dynamic. Eventually, they diverge.
And that divergence is where things go wrong.
That's exactly it. And the sources are very specific here. There isn't just one kind of drift. There are nuances that dictate how you fix it, or even if you can detect it in the first place.
So let's break them down. The source material highlights three specific types. The first one is data drift. also known as covariate shift.
Right. Covariate shift. This is probably the most common one, the one people run into most often. This is when the distribution of your input variables changes, but the fundamental relationship between the input and the output stays the same.
Okay, let's unpack that with the X-ray example. I need a concrete case here.
Sure. So imagine you trained your pneumonia detector using a data set from a specific high-end research hospital. These are high-resolution, perfectly lit, digital X-rays taken on brand new machines.
The best of the best data.
Exactly. The model learns patterns based on that specific visual language. It learns hazy spots in the lower lobes equals pneumonia. That's the rule it figures out from that pristine data.
Makes sense. That's the pattern.
But then you deploy the app to a rural clinic. They are using machines from the 1990s. The images are grainier, maybe the contrast is higher, or maybe the technicians there have a habit of positioning patients slightly differently, perhaps standing up instead of lying down.
So the inputs, the X-rays themselves, have shifted. They are now grainy and high contrast instead of crisp and digital. The world looks different to the model.
Exactly. Now ask yourself, does a grainy X-ray change what pneumonia is?
No. Pneumonia is a biological condition. It doesn't care about the camera resolution.
Exactly. The relationship between fluid in lungs and sickness is identical. That's the core concept, and it's stable. But the input space, the actual pixels the model is seeing, has shifted to a part of the statistical distribution it never saw during training. That's covariate shift. The model hasn't changed, the disease hasn't changed, but the window through which we look at it has become distorted.
And since it never learned what pneumonia looks like on a grainy 1990 scan, it fails. It's looking for crisp lines and finding noise, so it gets confused. How do we actually catch this? Do we just wait for the doctors to complain?
Well, you could, but if you wait for the complaint, it's already too late. You've potentially harmed patients. Ideally, you catch it mathematically before it causes problems. The sources mention a couple of statistical tests, the Kolmogorov-Smirnov test, or KS test, and the Population Stability Index, or PSI.
Those sound incredibly academic. What are they actually doing under the hood?
They do sound intimidating, but the concept is pretty simple. Think of them as comparing two shapes. You take a histogram of a feature from your training data, imagine a nice bell curve of pixel intensities, then you take a histogram of the same feature from the data coming in today from that rural clinic.
Okay, so I have two charts.
The KS test essentially overlays these two shapes and asks, what is the probability that these two sets of data came from the same source? It measures the maximum distance between the two cumulative distribution functions.
So it's a shape matcher. If the shapes are wildly different, it raises a flag.
Precisely. If the shapes don't overlap, if your training data is a curve on the left and your new data is a curve way over on the right, the probability drops to 0. That's your alarm bell. It tells you, hey, the data coming in today looks nothing like the data you studied for. Time to investigate.
So KS is the alarm system for the inputs. But that brings us to the second type of drift, which you mentioned is much, much scarier. Concept drift.
Yes. This is the one described as a silent failure. This is the one that really worries people.
Why is it silent? What makes it different from the grainy X-rays?
Because in concept drift, the input data looks fine. The KS test would pass, the inputs haven't changed. What changes is the relationship between the inputs and the outputs. The definition of the answer has shifted.
So going back to our example, this would be if the X-ray looks the same, but what? Pneumonia isn't pneumonia anymore. That doesn't make sense.
That's hard in medicine because biology is relatively stable, like you said. So let's switch to a behavioral example where this is rampant. Fraud detection or consumer behavior.
The classic example in the notes is pre-COVID versus post-COVID.
It is the perfect example. Think about an online retailer. They have a model predicting purchase behavior. They've trained it on years of data from, say, up to 2019. They know that a 30-year-old male living in a city browsing at 2 p.m. on a Tuesday is usually looking for, say, office wear, suits, maybe electronics.
Right. That's the pattern established in 2019. That's the truth the model learned.
Then March 2020 hits. The inputs are the same. It's still a 30-year-old male in a city browsing at 2 p.m. The demographic data hasn't shifted. Your input monitoring tools would say everything is green.
But suddenly he's not buying a suit.
No! He's buying sweatpants, sourdough starter, and a webcam.
The mapping from the person to the purchase broke. The underlying rules of society changed.
It broke completely. And here's why it's called a silent failure. The model doesn't know it's wrong. In data drift, the grainy X-ray, the model might be unsure. It might say, I don't recognize this image, and its confidence score drops.
Right, it gets confused because the input is weird.
But in concept drift, the model sees the input, the 30-year-old male, and recognizes him perfectly. It confidently predicts he will buy a suit. It has 99% confidence. It has no way of knowing that the rules of society have changed outside of its server room.
That is terrifying for an automated system. It's confidently driving off a cliff because the map says bridge here, but the bridge washed away yesterday.
Precisely. And that's why monitoring for concept drift is so much harder. You can't just look at the inputs. You usually need ground truth. You need to wait and see what they actually bought to realize your model is failing. There is a lag. You are always flying blind for a few days or weeks until the sales data comes back and you can compare predictions to reality.
So there's this window of failure where you're completely unaware.
A very dangerous window.
There is a third type mentioned in the notes, which I found really interesting because it feels like a detective story. Feature attribution drift.
This is a level deeper. This looks at the why. It's not just about what the model predicts, but how it's arriving at that prediction.
A why behind the prediction.
Right. Every model has features variables that it relies on. Maybe for a loan application, the most important features are annual income and credit score.
Sounds healthy. Those are logical predictors. If you have money and you pay your bills, you get a loan. Seems fair.
Right. But let's say you are monitoring your model using a tool like Eshay-Shapley additive explanations. We don't need to go into the weeds on SHAP, but it tells you mathematically which feature contributed most to the decision. It ranks them.
Okay, so it gives me a leaderboard of features.
Exactly. And let's say for months, annual income is number 1, credit score is number 2. All is well. Suddenly, you notice a shift in the SHAP values over time. Annual income is no longer the top predictor. Suddenly, zip code becomes the number 1 predictor for denying loans.
Oof. That sounds problematic. Potentially very illegal.
It's highly problematic, both ethically and from a technical stability standpoint. It signals that the model logic has shifted. It suggests the model has found a proxy. Instead of looking at the actual financial health income, it found a shortcut, zip code, that correlates with the outcome in the short term.
It's like the model is cheating. It found a shortcut and stopped looking at the actual financial data because the zip code was good enough for a while.
Exactly. And the accuracy might still be high. It might be correctly predicting defaults. But the reasoning has drifted. It's no longer making decisions based on the criteria you designed it for. That's feature attribution drift. It's the canary in the coal mine that your model is learning the wrong lessons, even if the final answer still seems right.
So we have established that reality is messy. Data shifts, concepts change, models get lazy and find shortcuts. This leads us to the next big question. If we want to fix this, or even just train these models in the first place, we need a way to measure these differences mathematically. We need to quantify how far our model is from reality.
We do. We need a ruler. But we aren't measuring the distance between 2 points on a piece of paper. We are measuring the distance between 2 probability distributions. And believe it or not, picking the wrong ruler can break your AI completely.
This brings us to part 2, the math of comparison.
Right. Let's talk about distances, or, more formally, distance metrics.
So let's conceptualize this. I'm a generative AI. I'm trying to create a fake image of a face.
Yeah.
I generate some pixels. I need to know, does this fake face look like a real face? I need to measure the distance between my fake distribution of pixels and the real distribution of pixels in the world.
And this is where we get into distance metrics. The choice of ruler determines whether your model learns or fails. It's that fundamental.
The first one on the list is a classic, KL divergence, Kullback-Leibler divergence.
This is the grandfather of information theory metrics. Conceptually, KL divergence measures information loss. If I try to approximate the complicated real-world distribution using my simple model distribution, how much information do I lose in that approximation?
It's a measure of surprise, in a way.
That's a great way to put it. It's the extra bits of information needed to encode samples from one distribution when using a code based on the other. It's used heavily in things called variational autoencoders, or VAEs.
Right, the VAE.
We don't need to get too bogged down in VAE architecture, but essentially a VAE tries to compress an image into a tiny code, a latent vector, and then expand it back out.
Like a zip file for images.
Sort of, but a fuzzy zip file. The VAE forces that tiny code to look like a standard bell curve, a Gaussian distribution. It uses KL divergence to measure how far is my current code from a perfect bell curve, and tries to minimize that gap, that divergence.
But there's a catch with KL divergence, a big one. It's asymmetric.
Yes, This is a crucial property that trips people up. The distance from A to B is not the same as the distance from B to A.
Which is weird, right?
Right.
In the real world, the distance from my house to the store is the same as the store to my house.
In physical space, yes. In probability space with KL divergence, no. K-A-A-L-Q-P. Depending on which direction you measure, the model behaves differently. One direction, the so-called forward KL, forces the model to cover all the data points, even the weird outliers, which leads to a blurry average. It tries to be everything to everyone.
Okay, so it averages everything out to be safe.
The other direction, reverse KL, encourages the model to focus on just the mode, the peak of the distribution, ignoring the outliers entirely. It becomes very confident about one specific type of outcome but misses the variety.
So using the wrong direction can make your generated images blurry or like all look the same.
Exactly. It averages out the details because it's trying to cover too much ground. Because of this asymmetry and some other mathematical quirks, researchers looked for something better, something symmetric, and they came up with Jensen-Shannon divergence, or JS divergence.
The smoothed version. Sounds nice.
Right. It's symmetric. Distance A to B equals B to A, and it's bounded between 0 and 1. It seems perfect. It's the polite, well-behaved version of KL divergence.
But there is always a but. It failed. Specifically, the notes mention it failed spectacularly for Jan's generative adversarial networks.
This is one of the great deep dives into why the specific math matters so much. Do you remember how a Jan works?
Roughly, you have a forger, the generator, and a cop, the discriminator.
Right.
The forger tries to make fake money, the cop tries to spot it, they fight, and they both get better.
Exactly. So to learn, the forger needs feedback. The cop needs to say, you are getting warmer or you are getting colder. That feedback is what allows the forger to improve.
We call that the gradient, the signal.
Yes, the gradient is the slope that tells you which way to move to get better. Now, here is the fatal flaw of JS divergence. If the distribution of the real images and the distribution of the fake images do not overlap at all, if they are completely different, which they always are at the beginning of training, the JS divergence is just a constant number. It's log 2, to be exact.
Wait, if the distance is just a constant number, it's a flat line.
Think back to calculus. What is the derivative, the slope of a flat, constant line?
It's 0.
Zero gradient.
So the cop just stands there. It has no advice.
The cop stands there and says wrong. It doesn't say warmer or colder. It just says wrong. The forger asks, should I change the color, the shape, the texture? And the cop just says wrong.
That is incredibly unhelpful. It's useless feedback.
It's the vanishing gradient problem. The forger has no idea which way to move to improve. So the model stops learning. It freezes. It dies.
And this happened because the MathJS divergence couldn't handle non-overlapping distributions. It gave no signal.
Correct. It was a mathematical dead end for early Jans, leading to all sorts of instability and training failures.
Enter the hero, the Wasserstein distance, also known as the Earth Mover's distance. I love this name.
This is my favorite metric because the analogy is so physical, so intuitive. Forget probability curves for a second. Imagine your two probability distributions are piles of dirt.
Okay. Pile A is the real data. That's the pile I want to build. Pile B is my fake data. That's the pile I currently have.
The Wasserstein distance calculates what is the minimum amount of work required to move the dirt from pile B to shape it into pile A. And in physics, work is defined as amount of dirt times distance moved.
So I have to figure out the most efficient way to move every shovelful of dirt from my fake pile to match the shape of the real pile.
Exactly. And the total effort of all that shoveling is the distance.
So even if the piles are a mile apart and don't touch, I can still calculate the work.
Yes, and that's the key. If the piles are a mile apart, the work is high. If they are an inch apart, the work is low. But here is the magic. As you move the pile closer, the work number changes smoothly. It gets smaller and smaller in a predictable way.
Which means it has a slope. It has a gradient.
It has a gradient everywhere. Even if the distributions don't overlap, the Wasserstein distance tells the forger, hey, moving the dirt this way reduces the work. It gives a direction. It says, you are still wrong, but you are closer than you were a second ago.
That is the breakthrough. It's the difference between wrong and warmer.
Exactly. That led to the invention of the WGN-Wasserstein-Jan. It solved the instability problem. Suddenly, we could train generative models that didn't just collapse, all because they switched from measuring difference, JS, to measuring work, Wasserstein.
That is such a cool example of how an abstract math concept translates directly to why does this AI actually generate a face instead of static? It's the engine room mechanics.
It really validates the importance of foundational math. You can't just code your way out of that problem. You have to math your way out. You had to change the fundamental ruler you were using to measure reality.
Okay, so we've covered the data with drift and the measurement with distance. Now let's talk about the training itself. Part 3, the engine room optimization.
This is where we talk about how the neural network actually learns, how it updates its brain based on the feedback it gets.
And according to our sources, it starts before we even show it any data. It starts with initialization, how you set things up at the very beginning.
Yes. When you first create a neural network, it's just a blank slate. You have millions of connections weights, but you can't just set them all to 0.
Why not? 0 seems like a good neutral starting point.
It seems logical, but if you set all weights to 0, every neuron does the exact same thing. They all output 0, the gradients are all the same. The network can't learn complexity because there is no symmetry breaking. It stays a dull, flat line. Every neuron is a perfect clone of every other neuron, and they never learn to specialize.
So we need randomness. We need to start them in slightly different places so they can find their own paths.
We need randomness. But not just any random numbers. The source material highlights 2 very specific men who changed the game, Xavier Glorot and Kaiming He.
Xavier initialization and He initialization. These are the 2 standards you see in every library. And the choice between them depends entirely on your activation function.
Let's break that down because it's a really neat piece of engineering.
In the old days, pre-2012, we used sigmoid or ton activations. These are those S-shaped curves.
Right. They squash the signal between 0 and 1, or -1 and 1. The problem is, as you pass a signal through many, many layers of a network, you want that signal to stay stable. You don't want it to explode to infinity or vanish down to 0.
Like a game of telephone. You want the message to stay clear and audible from the first person to the last.
Exactly. Xavier Glorot figured out that if you draw weights from a random distribution with a very specific variance, roughly 1 divided by the number of inputs, you keep the signal variance constant across layers. The volume stays steady. The message gets through.
So Xavier init keeps the volume steady for those S-shaped functions. It prevents the signal from getting too loud or too quiet.
Exactly. But then came a revolution. ReLU, the rectified linear unit.
The modern default, it's so much simpler. If the input is positive, keep it. If it's negative, set it to 0.
Simple, fast, and it solved a lot of other problems, but statistically it does something drastic. It kills half the data. Assuming your data is centered around 0, ReLU zeroes out all the negative values.
So it throws away half the signal at every single layer.
Which means it halves the variance. If you have a 100-layer network and you have the signal variance at every layer,
You have nothing left by the end. The signal vanishes. It becomes silence. The game of telephone ends with nobody hearing anything.
Exactly. Xavier init doesn't work for ReLU because it doesn't account for that halving. This is where He initialization, or Kaiming init, comes in. It's very similar to Xavier, but it multiplies the variance by 2.
It literally just doubles the variance at the start. That seems too simple.
It is that simple. It doubles the variance to compensate for ReLU, killing half the signal later. It's such an elegant, simple fix. Oh, we lose half. Let's start with double.
That is surprisingly practical. Almost like a hack.
But without that specific under-the-hood adjustment, modern deep learning with deep ReLU networks simply wouldn't train. You'd hit run and nothing would happen. The signal would die before it reached the output.
I love that. It's like, turn the gain up on the amp because the speaker's muffled. It's an audio engineering trick for a neural network.
Perfect analogy.
Okay, so we initialized correctly. Our signal is stable. Now we start learning. We need an optimizer, the thing that actually updates the weights.
The classic is SGD stochastic gradient descent.
And the source uses the ball rolling down a hill analogy, which I think is great.
It's the best way to visualize it. You are on a complex, hilly landscape. The height of the land represents your error or your loss. You want to get to the bottom, the lowest error. Gradient descent looks at the slope under your feet and takes a small step downhill.
But pure SGD has a problem. If the terrain is a long, narrow valley or ravine, it gets stuck or bounces from side to side. It's like a ping pong ball. It makes very slow progress down the valley.
Enter momentum. Imagine the ball has mass. It's a bowling ball now, not a ping pong ball. As it rolls down, it gathers speed. If the path zags slightly left then right, the momentum keeps the ball moving generally forward. It smooths out the noise. It crashes through the small bumps and dampens the oscillations in that ravine.
So SGD with momentum is a heavy ball rolling downhill. Much more stable.
Yes, but then we have the modern challenger, the one everyone uses, ADAM, adaptive moment estimation.
Atom is what you see by default now. If you look at a GitHub repo, it's almost always Optimizer Atom. Why is it so popular?
It is. Atom is clever. It combines momentum, the heavy ball, with something called RMSprop. Basically, Atom adapts the learning rate for each individual parameter.
Wait, so instead of one speed for the whole brain, every single connection, every neuron learns at its own pace.
Correct. If a parameter hasn't changed much, Atom boosts its learning rate. It hits the gas for that specific weight. If a parameter is fluctuating wildly, Atom slows it down. It's like giving every single weight its own personal, intelligent learning rate. It's incredibly fast at converging. It gets you to a solution very quickly.
There's a trade-off. The notes mention a sharp versus flat minima problem. This feels like a pro tip for the listeners.
This is a deep cut, but it's really important for people who want the best performance. Atom is fast, but it often settles into sharp minima. Imagine a very narrow, deep hole in the ground. You fall in, the error is very low. Great. But if your test data shifts just a tiny bit to the left or right, you're suddenly out of the hole and the error shoots up.
Okay. It's a precarious position. You're trapped in a tight spot, and it's not very robust to change.
SGD, because it's slower and has that momentum, tends to find flat minima. Imagine a wide, shallow valley. If you land anywhere in that valley, the error is low, and if the test data shifts a little, remember drift,
Yeah.
you are still in the valley. The error is still low.
So flat minima generalize better. They're more robust to change because there's more room for error.
Exactly, because they are more forgiving. So while Atom is the default for getting a good result quickly, for the absolute best state-of-the-art results, you often see researchers going back to good old SGD with momentum to find those robust flat valleys. It's the tortoise and the hare. Atom is the hare fast, but maybe stops in a weird spot. SGD is the tortoise slow, but finds the best resting place.
One last piece of the engine room before we move to frameworks. Regularization. This is about stopping the model from just memorizing the data, right?
Overfitting, yes. This is when the model learns the noise, not the signal. It gets 100% on the training data, but fails on new data it's never seen.
The two big ones mentioned are dropout and batch normalization.
Dropout is aggressive. It's beautifully simple. It's literally, during training, for every batch of data, randomly shut off 50% of the neurons.
Just kill them for a moment.
Temporarily. For each batch of data, you flick a coin for every neuron. Heads, you work. Tails, you're off for this round. This forces the network to not rely on any single neuron. It prevents co-adaptation, where two neurons become dependent on each other.
It's like a company where the boss randomly fires half the staff every day. The remaining staff has to learn to do everyone's job, just in case. They can't rely on their neighbor.
A brutal workplace, but a very robust one. If one person or neuron is missing, the others can fill in the gap. It effectively trains a massive ensemble of smaller, weaker subnetworks all at once. It's a fantastic regularizer.
And batch normalization. It has normalization in the name, so it's about stabilizing things.
Batch norm solves a problem called internal covariate shift.
We talked about covariate shift in the data, the X-rays changing. This is inside the model.
Right. Think about layer 10 in a deep network. The inputs to layer 10 are the outputs of layer 9. As layer 9 learns and changes its weights, the distribution of data flowing into layer 10 keeps shifting. Layer 10 is constantly chasing a moving target.
It's trying to learn, but the ground keeps moving under its feet. That sounds impossible.
Exactly. Batch norm fixes this by forcing the inputs of every layer to be normalized, to have a mean of 0 and a variance of 1. It stabilizes the landscape. It says, no matter what layer 9 does, I will make sure the data entering layer 10 is centered and scaled.
It paves the road so the car can drive faster.
And it allows you to use much higher learning rates without the network exploding. It was a huge breakthrough in 2015 that allowed for much deeper networks to be trained effectively.
All right. We understand the drift, the distance, and the optimization. Now we have to actually write the code and run it. Part 4. The builder's frameworks and hardware.
This is the holy war of AI, the great debate.
PyTorch versus TensorFlow JAX.
The battle of the graphs. It sounds abstract, but is a very practical distinction.
Let's explain dynamic versus static graphs, because this dictates the daily life of an AI engineer.
Okay. PyTorch uses dynamic graphs. This is defined by run. It means the graph, the map of the neural network, is built on the fly as the code executes line by line.
Like interpreting a script in real time. The computer doesn't know what line 10 is until it has finished line 9.
Yes. It's very Pythonic. You can use if statements, for loops. You can stick a debugger anywhere. If your code crashes, it tells you exactly which line. It's incredibly developer-friendly. It feels like writing normal code, which is why researchers absolutely love it.
And static graphs. like the old TensorFlow 1.x or the newer JAX.
That is define and run. You define the entire architecture first. You build a complete blueprint of your factory. Then you hand that blueprint to a compiler. The compiler looks at the whole thing, optimizes it, locks it down, and then you start pouring data into it.
What's the advantage of that? It sounds so rigid and difficult.
Speed and optimization. Because the compiler sees the whole graph at once, it can do really clever things like operator fusion.
Operator fusion. Sounds cool. What is it?
Imagine you have a recipe. Chop onions, then saute onions, then add garlic. In PyTorch, you do each step separately. You take the onions out of the fridge, chop them, put the knife away, take out a pan, saute them. In a static graph, the compiler says, hey, let's fuse these. You can chop the onions directly into the hot pan.
Okay, so in math terms, what's happening on the chip?
If you have a matrix multiplication, then a bias add, then a ReLU activation. In PyTorch, that might be 3 separate trips to the GPU memory to fetch and store data, which is slow. In a static graph, the compiler can say, hey, let's fuse these into one single custom kernel. 1 trip to memory to do all 3 operations. It's much, much faster.
But the downside is debugging.
It's a nightmare. Because the error happens inside the compiled graph engine, not in your Python script. The stack trace is usually gibberish. You lose the ability to easily inspect what's happening step by step.
So PyTorch won the hearts of researchers because of flexibility. But static graphs, like JAX, are making a comeback for pure speed and scale, especially in production.
Exactly. When you are training a massive model for months, that 10% speed up from operator fusion saves you millions of dollars in electricity and time.
And speaking of scale, that's the next big topic. What happens when your model is too big for one computer? Or your data set is too big?
Distributed training. This is where engineering takes over from math. This is about building supercomputers for AI.
There are 2 main ways to slice this pie, right? Data parallelism and model parallelism.
Let's start with data parallelism. This is the standard, the most common approach.
How does it work? Let's say I have a huge data set and 8 GPUs.
Okay. You have a huge data set. You have 8 GPUs. You copy the entire model into every single GPU. So you have 8 identical copies. Then you give each GPU a different slice of the data. They all process their slice simultaneously.
They all calculate the gradients based on their piece of the data.
Right, but now they disagree. GPU 1 says move left. GPU 2 says move slightly left. GPU 3 says move right. You need them to sync up and agree on one update.
They average them.
They average them. They perform an all-reduced step where they communicate, average all their gradients, and then every model updates its weights with that same averaged gradient. Then the cycle repeats.
But there is a nuance here mentioned in the notes regarding Python specifically. DP versus BDP? This sounds like jargon, but it's important.
Ah, yes. The Python GIL, the Global Interpreter Lock.
The villain of Python parallel processing.
Python was designed in the 90s for simplicity, not for massive parallelism. The GIL ensures that only one thread executes Python bytecode at a time. It prevents race conditions, but it kills true parallelism in multi-threaded programs. Standard data parallelism, or DP in PyTorch, uses threads. But because of the GIL, Python can only execute one thread at a time, so you get a bottleneck.
It's like having 8 lanes on a highway, but only 1 toll booth.
Exactly. The GPUs are fast, but Python is slow at handing out the work and coordinating. DDP, distributed data parallel, fixes this by spawning separate processes for each GPU. Each process has its own Python interpreter. There is no shared GIL bottleneck.
So instead of 8 threads sharing one clogged-up brain, you have 8 separate brains working independently.
Correct. It's significantly faster and is the industry standard for any serious multi-GPU training.
Okay. But what if the model itself is too big? We're talking about these large language models now. They can be hundreds of gigabytes. They don't fit on one GPU. You can't copy the model 8 times if it doesn't fit once.
Then you need model parallelism. You have to break the brain apart and spread it across the GPUs.
How do you slice a brain?
2 main ways: pipeline parallelism or tensor parallelism.
Pipeline is vertical, like an assembly line.
That's a great way to think of it. It's slicing by layers. If you have a 24-layer network, you could put layers 112 on GPU 1. You put layers 1324 on GPU 2.
So the data goes to GPU 1, gets processed halfway, then the output of layer 12 gets handed off to GPU 2 to finish the job.
Exactly, like an assembly line. The big problem is the bubble. GPU 2 sits idle while GPU 1 works on the first batch, so you have to be clever with scheduling, sending multiple small batches in a stream to keep everyone busy. But it allows you to fit a much bigger model.
And tensor parallelism, that sounds even more complex.
That's slicing horizontally. You are splitting the matrix operations themselves.
Wait, you're splitting a single math problem across multiple chips.
Yes. If you have a massive matrix multiplication, which is 99% of deep learning, you might give half the rows of the matrix to GPU A and half to GPU B. They compute their parts simultaneously and then communicate to combine the result.
That sounds incredibly difficult to coordinate. The communication must be insane.
It is. This is how things like Megatron LM are trained. It's incredibly complex engineering because the communication between GPUs has to be lightning fast. If the GPUs are waiting for each other to share results, the whole thing slows down. You need high-speed interconnects, NVLink, infinite band. It's a hardware problem as much as a software one.
It's amazing to think about. We started with, does the cat look like a cat? And we ended up with splitting a matrix multiplication across multiple graphics cards using process-based parallelism to avoid a Python interpreter lock.
That is the deep dive. It shows you the depth of the stack. It's not just import torch. It's physics, it's calculus, and it's massive scale systems engineering.
So let's bring it all back home. We covered a lot of ground. It feels like we just rebuilt an engine.
We did. We started with drift. The realization that models fail not because they are broken, but because the world changes. We talked about covariate shift, the data looks different, and the scarier one, concept drift, the rules changed.
Then we looked at the math. We saw how the wrong ruler, JS divergence, killed Jans with vanishing gradients, and how the Earth mover's distance, Wasserstein, saved them by providing a gradient even when distributions don't overlap. We learned that measuring work is sometimes better than measuring difference.
We went into the engine room. We saw why He initialization exists to save the variance from being killed by ReLU. We discussed why we use momentum to roll past the bumps and why the flat minima found by SGD might be better for generalization than the sharp ones found by Atom.
And finally, the machinery. The trade-off between flexible PyTorch and fast static graphs, and the massive scale of distributed training, slicing up data, and even the models themselves.
So what for me here is this. Deep learning isn't magic. It is a chain of very specific, very intentional mathematical and engineering choices. When a model fails, it's usually traceable to one of these fundamentals. Did you pick the wrong metric? Did you initialize wrong? Did you ignore drift?
It's not a black box if you have the schematic.
Exactly. It's a machine. A complex one, but a machine nonetheless. And you can debug it if you understand the parts.
Before we go, I want to leave the listener with a thought. We talked about concept drift, the silent failure. The model is confident but wrong because the relationship between input and output has fundamentally changed.
Right. The model doesn't know what it doesn't know. The map is no longer the territory.
We are currently building systems agents, automated decision makers, that are larger and more autonomous than ever. We are handing over more control to these systems in finance, medicine, transportation. If concept drift is truly silent, how many silent failures are happening right now inside these massive black boxes that we simply don't have the metrics to detect yet?
That is a question that keeps me up at night. As systems get more complex and interact with the world in more ways, the silence of the failures might get deeper. We might need a whole new kind of math, a new kind of ruler, to even hear them.
On that cheerful note, thank you for joining us on this deep dive into the math and machinery of deep learning.
Thanks for having me. It was a lot of fun.
And thank you for listening. Keep learning and check your distributions. We'll see you next time.